In this video, we will demonstrate measuring wideband reference antennas using the mirror method. In this method, time domain is utilized in the vector network analyzer. The time domain considerations are the resolution, delta distance, which is approximately given by 0.6 over the bandwidth in gigahertz. The aliasing free region, which in distance is given by approximately 0.15 over the delta frequency step, and that distance is in meters. The Diamond Engineering reference horn was measured from a frequency band of 0.7 gigahertz to 26 gigahertz with 1600 data points. A beam scan was performed with an as-el start-stop step of -40 to +40 degrees in steps of 5. The basic mirror setup is shown as the horn on the DAMS FSM 518, the DAMS horn mirror measurement mirror at a distance of 0.5 meters. The overshoot of the main beams is corrected by measuring the efficiency and measuring the efficiency over the extents of just the mirror. Those two efficiencies as a ratio form a correction factor. The overshoot is naturally a function of the distance from the mirror and the height and width of the mirror. The Diamond Engineering standard mirror is 24 inches square, or approximately 0.6 meters. The use of the mirror provides the mirror image of the test AUT on the opposite side of the mirror. This enables a classical two-point measurement with an identical clone. Since this measurement has already been made, we'll load it from the Advanced Data Directory, the file de700_26.dat. When we load that file, we see the new measurement, the raw data, made by an Anritsu vector star VNA in data 1. We'll invoke the network simulator and load the mirror time domain S11 gain measurement schematic. In this schematic, we see a path, the measurement data, a math function, and a correction for the mirror. Because we're in S11 mode, we must divide the path attenuation by 2. That's equivalent to just removing the reverse path. So we have only one path to deal with. The net gain of the antenna is again doubled, and we must divide that by 2. Hence the math icon, which can support any math and access the internal variables, is simply the square root. The mirror is given by height by width in dimensions of path loss, which in this case are meters, and 0.6 by 0.6 meters. The material of the coating is aluminum. Now that we have the measurement data loaded, we note that almost 500,000 data points were used in this measurement. For good resolution and alias free, it's necessary to have a lot of measurement data points. 462,000 data points exceeds the simulator's capacity. The capacity of the simulator is 150,000 data points. The capacity of the dam's measurement system is 500,000. So it's very close to the upper limit. To reduce the size of this data set, we're going to recall the data set, and we're going to go into the register utilities and utilize select frequency points. Because this data is 0.7 to 26 gigahertz, I'm just going to take 27 data points, and I'm going to shift those data points to reg 0 and exit. I'll store that data in register 2, and we see that over that frequency span, the large data set is reduced to simply 7,800 points. Next, we'll invoke the path loss module and set the path loss to 0.5 meter. And we'll change the register icon to register 2, and everything is set. We'll invoke the plot, and we'll change the scale from 0 to 20 dB. And we're ready to calculate the reference horn gain. To do so, we simply invoke S21, and once completed, we go to the calculator and invoke max. Going to max positions the azimuth and the elevation slider to the maximum signal, which in this case was at 0, 0. We can see that the reference antenna extends from 700 megahertz to 26 gigahertz with monotonically increasing gain. This gain has been verified using 2- and 3-point methods. It does not replace the classical calibration lab. It is still necessary to have your horn precisely calibrated in an official calibration lab. However, these numbers generally overlay Cal Lab data. We can now ask ourselves, what correction was the mirror responsible for? To do that, we'll invoke the hold and we'll recalculate the gain. In the correction mirror icon, that calculated gain is set for the purpose of overlaying the two. And here we see the gain without the mirror and the gain with the mirror as a correction. And it should be mentioned that using the mirror reflection method requires a wide band of measurement with a lot of frequencies. Because of that, it's not possible to measure narrowband antennas due to the fact that too much of the signal content never really reaches the antenna. Some discretion must be used in deciding frequency starts and stops, as well as resolution, and the type of antenna that's being measured. An antenna with a poor match at one or more frequencies can create significant error. The Diamond Engineering 726 horn has excellent match over this entire frequency range. I hope this sheds some light on the use of the mirror for wideband measurements.